Hello again. This video is meant to cover section 3.5b in your textbook. Now that we understand what a function is and how to determine if a relation is a function or not, the next thing we often do is try to determine what a function's domain and range are. You'll see that we focus a little bit more on domain than range. Range is the harder of the two. We will look at range in a couple of simpler examples, but we'll always be looking for domain. It turns out to be a pretty important thing. Now before we dive into finding domain and range, let's talk a little bit about function notation. So let's say that we were to start with, just one moment, let me turn on my editing here. Let's say we were to start with a relation like y is equal to 2x plus 3. We could go through and think about what happens when we pick a value for x and plug it in, and what kind of value of y do we get back out again. And our expectation is that for each and every distinct value of x that we plug in, there's only one answer for y. And since each x corresponds or relates to only one y, this is a function. And once it's a function, we can give it a name. A common name for functions is f for function. Pretty creative. And then what we like to do is say, what is our input variable? What is the independent variable? In a relation like this, the input is going to be x. So we put that in parentheses after the f. Now, this doesn't say that we're multiplying anything. This is a new type of symbolism. And it is read f of x. And what that really stands for is the value of f at the value x. And x represents our input. Let me write that over here on the side. X equals input. And the whole symbol f of x represents the output. And again, f is the function's name. And we can use other letters too. We'll see g and h used quite a bit. Right. So it's important that we understand what this notation is and how to read it. So we could write f of x is equal to 2x plus 3. And if you see something written like f of x equals something, or g of x equals something, or h of t is equal to something, we can use different letters in different variables, you immediately know that someone has done the work to determine that yes, this is a function. All right, now that we've talked a little bit about that, let's take a look at example 1. Starts right here. This is all on page 165 in your textbook, by the way. Given the function g, so there's our function's name, defined as g of 1 equals 2, g of 3 equals 4, g of 5 equals 6, g of 7 equals 8, and g of 9 equals 0, what is the domain and range? So our function's name is g, and it gets repeated over and over and over again as we go through here. And remember, what's in the parentheses is the input. So this 1 is an input, this 3, this 5, this 7, and this 9. And input values are domain values. So the domain of the function is going to be what we see right here in the curly braces, 1, 3, 5, 7, 9. We put the curly braces around it when we have specific numbers. It's not all the numbers in a range. It's only the numbers 1, 3, 5, 7, and 9. No other numbers, no numbers in between them, etc. We generally try to write our numbers in the same order they would appear on a number line from left to right inside those curly braces while we do that. For the range, let me change colors. For the range, the output is represented by the whole g of whatever. So g of 1's output is 2. G of 3's output is 4. G of 5's output is 6. G of 7's output is 8. And G of 7's output is 9. And we could write that as we see here in curly braces 2, 4, 6, 8, 0. It's actually slightly better to write it as 0, 2, 4, 6, 8. Using those curly braces on each side. And that's so we write things as we see them from left to right on a number line. What would we do if, for instance, we had a number show up twice? Let's say that we had the same output value for two different input values. When you write your range, you would only write that output value once. In other words, in between the curly braces, we should never repeat anything. We should only put numbers one time. No matter how many times they show up, no matter how many times they're used as output for the function, we only put them once into our range. All right, example 2 starts right here. It says, given the function f defined as f of x is equal to x plus 1, what is the domain of f? Well, here we don't have specific numbers. Here we actually have an entire formula. So how are we going to deal with that? All right, f of x equals x plus 1. Well, we're really interested in the x plus 1 part over here. This is kind of the rule that allows us to take x values and turn them into y, or f of x values. And what we do is we begin by assuming all real numbers work. And then we're going to see if we can think of any numbers that don't work. So in this situation, is there any number that we can't add 1 to and get an answer back? If you think about that for a little bit, I think you'll come to the conclusion that there aren't any numbers like that. We can take any number we can imagine and add 1 to. We can add 1 to 1, we can add 1 to a half, we can add 1 to -4, we can add 1 to pi. We can take any number and make it one bigger. So we start by assuming all real numbers work. We try to see if there are any that don't, that break our function. In this case, there aren't any. So we end up with the answer of all real numbers. They've written it with this r here, so you could write r, or you could write all real numbers. If you write all real numbers, make sure you include the word real. All numbers is incorrect. All real numbers is what we want to write there. All right, example 3. Given the function g, defined as g of x is equal to 1 over x, what is the domain of g? So we start once again by assuming all real numbers work. And then we look to see if we can find any that don't. Well, in this case, if I plug a 0 in for x, 1 divided by 0 is undefined. So 0 doesn't work. Anything else works. We can divide 1 into all sorts of different numbers of pieces, and everything's fine. But we don't know what it means to divide something into 0 pieces. So 1 divided by 0 is undefined. So our answer then is all real numbers except for 0. All right? The only things we know of right now that break a function are essentially trying to divide by 0, or if we potentially try to take the square root of a negative number. And you'll notice we haven't seen any square roots in this course so far. We're not going to, so that's not going to be something we need to keep an eye out for. So the one thing we need to keep an eye out for is dividing by 0. So let's take a quick look at just a couple of slightly different functions. Oops. All right, I'm going to consider h of x is equal to 1 over x plus 1. Its domain is going to be all real numbers. That's what we assume to start with, except -1. Why -1? Well, -1 because if we plug -1 in for x, we will have 1 over -1 plus 1, which is 1 over 0. We get the divide by 0 problem. So -1 is the number that causes us to try to divide by 0, so it's the number we want to leave out of our domain. Let's say we had something like f of x is equal to 3 divided by 2x minus 5. Our domain here would be all real numbers. That's what we start by assuming, except in this case our except is going to be 5/2. And that's because if we look at 3 over 2 times 5/2 minus 5, we'll end up with 3 over 5 minus 5, or 3 over 0. So 5 halves is the number that makes the bottom 0. It causes us to attempt to divide by 0, which we can't do. It's undefined. So we have to make sure that number is excluded from our domain. We say all real numbers except 5 halves. How did I find that? Well, what I did was I took the denominator, 2x minus 5, and I set it equal to 0. I specifically decided to look for what value of x makes the whole denominator 0. And we can solve that. We can add 5 to both sides, giving us 2x equals to 5. And then if we divide both sides by 2, we find x equals 5 halves. Since x equals 5 halves is the value that makes the denominator 0, it's the number we have to exclude from our domain. Also, briefly notice here that what's going on in the numerator doesn't affect anything. We don't really care what's happening in the numerator, only the denominator. And we just want to make sure that our domain never lets the denominator be 0.